Folks, I'm sorry, but I've been lying to you. I've been lying to you about electrons, and it breaks my heart. It's time for you to know the truth. The truth is, what we think we know about atoms, like this picture of a Bohr atom right here, boron rather. This is a Bohr diagram of boron. So boron, Bohr diagram. Bohr diagrams, by the way, were named after a guy named Niels Bohr. That's why they're called Bohr diagrams. And in his day, about 100 years ago, all the experiments he had available pointed to this being what atoms really looked like. And in his mind, there was a nucleus in the middle, and spinning around that nucleus were the electrons, like planets around the sun, orbiting. And so this was called the orbital model of the atom. Well, pretty soon after Niels Bohr, along came this new guy that did some new experiments and really some amazingly brilliant, fancy math. His name was Erwin Schrödinger. And his experiments and what he realized was, look, this isn't the real picture. In fact, the real picture of an atom, which we still use today, by the way, about 100 years later, the real picture is much more complicated than this. Like, this just doesn't do the trick. So what I have here is a video that kind of shows a comparison of the two. We've got a nucleus in the middle, and it's going to show an electron spinning around in an orbital around that nucleus. But pretty quickly, it's going to switch to the view of Erwin Schrödinger's model, which looks like this. And this is also called the quantum mechanical model. And you see, the electrons, they're not spinning around. They kind of make a cloud. I think I mentioned this in one of my earlier videos, that we often say electron cloud. Now, the thing that's really freaky about this model is that this is not lots of little electrons. This is a picture of one electron. You see, electrons aren't little particles. In fact, electrons exist in large regions of space all around the nucleus, all at the same time. Quantum mechanics is wild, okay? But our experiments have shown hundreds of times over and over again that this is really what's happening. Here's a picture of an atom like boron, where we have two shells. So you can see so far this picture is somewhat similar to the Bohr model, right? We've got one shell in the middle, and here's one shell in the middle, and then we've got another shell with 3 more electrons on the outside. The big difference is that thing that I told you, like when you look at the cloud model, you can't really tell how many electrons are in there just by looking. Now, it gets more complicated than this too, right? In this movie, it's showing bigger and bigger atoms. Here's one with 4 energy levels. Here's one with 5 energy levels. And all the clouds are spheres in layers like an onion. But in fact, with some bigger elements, the clouds stop looking like spheres too. For example, here's a very common electron cloud shape that we see in elements. This is called the dumbbell shape, and that's got 2 blobs, one on top, one on bottom. But again, that cloud with 2 blobs, that's 1 electron. Right here, this is 1 electron, and it makes that whole cloud shape. Okay, so again, you got to stop thinking about electrons as little tiny particles. Here's another cloud shape that we observe in atoms, 2 blobs with a donut going around the middle. If I go to ptable.com, we can see even more complex things. But we can see with boron, by the way, here's the first ring. Here's the second energy level. 2 of the electrons in the second energy level look like a sphere, but that third electron in the second energy level is that dumbbell shape. If I go to really big elements, you can see there's all sorts of weird cloud shapes, okay? So my point is, what's my point? The reality of the shape of an atom, okay? Because the shape is the electron cloud, right? Because that takes up most of the space. The nucleus is just a little ball in the middle. The reality of the shape of an atom is much more complicated than we think with these pictures. And really, these pictures just don't do the trick anymore. We need something better. Problem is, good luck drawing all this stuff that I just showed you, right? I'm not going to draw all these. All these different shapes that I just showed you, all of this is in one atom of gold. So I would have to draw all this at the same time. And that's just not going to happen. So what we have now that's better than a Bohr diagram is called an electron configuration. Okay. So for your notes. An electron configuration isn't a picture anymore. It's a code. And that code has numbers and letters in it. And the code tells us where all of the electrons are in any element. Okay. I'll give you more details. So Niels Bohr, he discovered the major energy levels, the shells. But Erwin Schrödinger, when he got into that more detailed calculations, he discovered that, wait a second, the second shell is actually two subshells that are very close together in energy. The third shell is actually three subshells that are very close together in energy. So, again, we need something better than this picture. The configuration can do that for us. So starting now for the second half of the video, I'm going to show you some electron configurations. I'm going to teach you the rules about how to read them, and that'll be our introduction. Okay. Now what we have here is I have three pictures. I've got a boron, a carbon, a nitrogen. Here's the Bohr diagrams on top, and these codes down here, these are the electron configurations. Okay, so what you'll notice is there's three basic pieces to an electron configuration. Let's see if I can move this aside for now. You've got the big giant numbers. Okay, so let's just copy this one down here. 1s2, 2s2, 2p1. The big giant numbers, those are called coefficients. They tell which energy level we're in. Okay. Or shell. So this number 1 right here is telling me, hey, there's some electrons in the first energy level. Then you've got a couple of big 2's here. Those coefficients, those big 2's here and here, those tell me I've got some more electrons in the second energy level. Okay, then we've got the letters. And that's going to get sloppy. How do I... the letters. S and P. Those letters tell us about the subshells. Okay, so as I set up here, first major shell has one subshell. That's the 1s. And you can see down here that the beginning of boron says 1s. The second shell, though, is divided into two subshells. One of them is called the 2s, and the other one is called the 2p. And you can see in the electron configuration for boron, there is a 2s and a 2p. So this is saying we have some electrons in the 1s, we have some electrons in the 2s, and we have some electrons in the 2p subshell. So again, you see it's like a laundry list telling us where all the electrons are. Finally, the superscripts. That is the number of electrons in a subshell. Okay, so 1s2, 2s2, 2p1 is saying I've got 2 electrons in the 1s subshell. I have 2 electrons in the 2s subshell, and I've got 1 electron in the 2p subshell. Now, I just threw a lot of information at you. We will have several days to grapple with this. Right now, I just want to help you to understand how to identify elements. Okay. Now, you know, with the Bohr diagram, you can just count electrons, and that'll help you to identify an element. And you can see here there's 1 electron, so that must be hydrogen. Because if we look at the periodic table, hydrogen is atomic number 1. It has 1 electron. Without a Bohr diagram, though, you can still count electrons. Okay, 2 electrons plus 1, because remember, the superscripts tell us the number of electrons in each subshell. So if I add those up, 2 plus 1, I get 3 electrons. And number 3 on the periodic table is lithium. Double check that. There's the number 3. It's lithium. Okay. So that time I didn't use the picture. Same thing here. I'm just going to add up the superscripts. 2 plus 2 plus 6 plus 1 equals 11 electrons. I go to my periodic table. Number 11 is sodium, Na. And so now I have figured out, using the electron configuration, which element it is. So just one last thing to wrap this up. This says, in the 1s subshell, I have 2 electrons. Here they are, 1s, 1s. In the 2s subshell, I have 2 electrons. 2s is the second energy level. So here's a 2s, here's a 2s. In the 2p subshell, there's p's, there are 6 electrons. So look, we're still in the second energy level, the coefficient tells us. So there's a 2p, 1, 2, 3, 4, 5, 6. Those are the 2p electrons. And finally, there's 1 electron in the third energy level in an s subshell. So there it is, 3s. So you see, everything in the configuration does match up with the Bohr diagram. It just gives us that extra detail of the subshells. And if we are so inclined, we can go look on ptable.com to see the actual shapes. And we can see that same information with the pictures as well. Good job. Tough topic.